Welcome back to elementary statistics. In this video, we're going to be talking about visualizing data. In order to visualize some data, we need some data to talk about first. And we're specifically going to be looking at a categorical frequency distribution for most of this discussion. There's the right button. So here I have a set of data. We have 5 days, Monday, Tuesday, Wednesday, Thursday, Friday. We have data points going along with each of them, 13, 21, 33, 52, and 81. Unlike the categorical frequency distribution we looked at in the previous video, notice that this one has ordinal data. In the last video, we were looking at colors of candy-coated chocolate, which came in nominal data form. Right? Being ordinal data is going to open up a few more possibilities for us. And I'm here in spreadsheet software instead of trying to draw things because my goal here is to talk about a couple of graphs and charts. And spreadsheet software is really good at producing graphs and charts really quickly. This is not necessarily a lesson in how to produce graphs and charts because your spreadsheet software might not be the same as mine. But what I want you to take away from this is not only how to read graphs and charts if you're not familiar with it, but also how to make decisions on which graphs and charts might be useful. All right, let me get my head out of the way. There we go. And let's put a bar graph on the screen. All right, here we go. A pretty typical bar graph, which is kind of the workhorse of statistical graphs. Bar graph is your kind of default option. If you're not sure what kind of graph or chart is appropriate for the data you're looking at, a bar graph is never the wrong choice. It's not always the best choice, but it's never a wrong choice. Of course, on a bar graph, the height of each bar corresponds to the value of that. So Monday had a value of 13. 13 is right here, somewhere between 10 and 20, exactly what we would expect. Great, there we go, get my head back out of the way. Of course, we don't need our bar graph to come in column. Very frequently, you'll see a bar graph where the bars come across in rows. Bar graphs set up like this, I find to be very useful when we have categories that are a little bit longer, right? It gives you more space over here to put the label of each category. You can make that a little bit wider compared to when you had it at the bottom, and the bigger the label was for each bar, the further apart the bars were. All right. So we have this kind of row-shaped bar graph. It works much the same. Instead of having our vertical position, we have a horizontal position, but it's still equally readable. Everything is happy. Other options, pie graphs, pie charts are very friendly. And so we can use a pie chart to our advantage here. Sometimes you will see people really enjoy the exploded pie chart. I really, really hate these. Pie charts should have everything kind of lumped together here. Oops, sorry about that. There's the button I wanted to push. One of the things I like about pie charts is that they allow us to talk about a part of a whole. Sorry about that. One of the things I really like about pie charts is the way that they present portion of a whole. The bar graph is really good for comparing two different data points against each other. The pie chart is really good for looking at how each percentage works. So if we calculate the percentage on each of these, we'll see Friday at 81 is a pretty significant percent, and that represents this very large area. So Friday is a significant part of the overall, Thursday a little bit less so, Monday is a relatively small piece of the overall. It's very difficult to compare Monday and Tuesday. Sure, we can see that Tuesday is bigger than Monday, But that's not something that a pie chart is very good at talking about. Pie charts are specifically good at talking about this is a small piece of the overall, this is a large piece of the overall. If that's what you want to focus on, go for the pie chart. Uh, Coming back to our bar graph, again, the difference here, we can see if we want to compare Monday and Tuesday. Certainly Tuesday is more than Monday, but it's not twice as much as Monday. Um, we can get a good sense that Wednesday is about twice as much as Monday just by looking at the pictures. Those are things that bar graphs will highlight that a pie chart cannot. Since our data is time-based data, it might be interesting to see how the data evolves instead. And so we can look at a line graph with an actual line. There we go. I like line graphs to talk about how things change. All right, so we're going from Monday to Tuesday to Wednesday to Thursday to Friday. If we're looking at something that is changing over the week, we can see that the change is relatively shallow here. And one of the interesting features of this graph is the change gets steeper and steeper. So a line graph is very useful when we're talking about how things are changing as a way of comparing the difference between 2 points rather than the points themselves. While we're looking at these graphs, I want to point out a couple of key features that you should always pay attention to. First of all, and very notably, no matter what your data looks like, you should make sure that you have a legend for the scale and that the scale starts at 0 and that the space between two sequential numbers are always the same. That is not something that always has to happen. We're not going to get enough into thinking about data in this course, but as you think about data, as you think about applications of data in applied sciences, social science, or natural science, you start to understand when that can be useful. But it is rare that it is useful. And that's important because when you are missing those things, it's a great way to lie about the data. And so one important thing in looking at statistical graphs is understanding what they are saying, and even more importantly, what they are not saying. Let's go back to my notepad, and I'm going to draw a very simple graph, a very simple bar graph to be specific. Right? If more is better, and I don't know what the application is, I'm not even going to think about that. If more is better, I think that you will agree that B is a significant jump over A, or at least it certainly looks that way. Until you see labels on these and you realize that graph A is at 3,060,000. And bar B here, I'm sorry, I wrote the wrong number down. I wanted 6,030,000. And bar B is at 6,090,000. Because I hid the legend on this graph And in fact, it is measuring starting at 6 million and counting by 10,000. Certainly, there's a difference between 6 million 30,000 and 6 million 90,000, but it's not really much of a difference. If I redraw this graph using an honest scale with 0 at the bottom, and counting by millions, so 1 million, 2 million, 3 million, and so on, then graph A oops, let's go a little bit further. Uh, bar A is going to look something like that. And bar B is going to look something like that. It's hard to tell the difference between those two graphs when they are presented using an honest scale. And that's something that is very important. Another thing that people love to do in order to try to be deceptive about how they are presenting data is to use what's called a logarithmic scale. And again, there are places where logarithmic scales are incredibly important and useful. But a logarithmic scale means counting by multiples instead of by adding. We start at 1, then 10, then 100, 1,000, 10,000, and so on. Let's put one more on this one for good measure. All right, so here we have A, B, and C. And the way that I have drawn this, thanks to the logarithmic scale, sure, B is larger, A is smaller, but they seem to be relatively similar in size. But of course, that's a lie. And if I try to draw this using a reasonable scale, it's in fact very difficult. Oops, that's too far up. That'll work. All right, so here I have a scale, which again starts at 0 at the bottom, which is important. And it's going to count up by steps of 10,000. So 10,000, 20,000, 30,000, 40, 50, 60,000, 70, 80, 90,000. And if I try to draw these three graphs using this scale, there's A. Let's try that again with a straight line. There's B. And here's C. I hope that you will agree with me that this first graph is incredibly misleading if this is the data that we want to present. This particular example, I didn't pull the specific numbers because I've lost access to it, but about 10 or 15 years ago, there was a publication about from the British government trying to argue that their spending on education, on health care, and on the military was about equal. They did so by creating a logarithmic scale graph, which hid this kind of a discrepancy between military spending and education spending. Um, as you might expect, statisticians were in a bit of an uproar. I mentioned these ideas on misleading graphs, not to try to teach you how to create a misleading graph, but to how to spot a misleading graph. If data is being presented to you and it's being presented in a graphical form, you want to be able to digest that data quickly. You want to be able to look at it, look at the scale, and trust that your bars are going to be representative, that your areas are going to be representative, that things will make sense to you very quickly. But if the data is presented and the scale is not there, then you have to question things. You have to look at it carefully and verify for yourself that, yes, this is following a reasonable scale. If it's not, that means that somebody made the conscious choice to create a graph that would lie to you. And if they're going to lie to you about that graph, what else are they going to lie to you about? Before I wrap up on this video, I do have one other topic, one other type of graph that I want to look at today. It's not, oh, sorry, hitting the wrong button. Right. This last type of graph is not one we're going to use too much in this course. We will try to get to it at the end of the course, but I like to mention it because for any of you who are going onward to take laboratory science courses, the scatter plot is the most important tool in many of those fields. So a scatter plot is a way of organizing what we call two-parameter data. And in order to talk about that, I'm going to talk you through a very simple physics experiment. I am going to take and build a ramp, which might look something like this. I'm going to place an object, a marble, on the ramp, and I'm going to let the marble roll down the hill. While it's doing that, I'm going to have a stopwatch, and I'm going to mark down at 1 second, 2, 3, 4, and 5. How far has this marble gone? Maybe it went 3 centimeters, and then 6 centimeters, and then 10, and 15, and 21. Then I'm going to do this with another marble, starting at a slightly different place on the hill. So I'm going to get more data, which is going to be the same times 1, 2, 3, 4, and 5. Only with this second marble, I went 2 and 5, about 9, 14, and 20. Now I want to compare these two sets of data. I can do that using a scatter plot. So we'll set up a scatter plot. It will have axes of time and distance. I think that counting distance here by 5 might be appropriate. How about by 3? 3, 6, 9, 12, 15, 18, 21. And then counting time by 1. We can plot these points at time 1, distance 3, at time 1, distance 2, at time 2, distance 6, at time 2, distance 5. And then we had 10 and 9, and 15 and 14, and why am I so bad at this? I blame this touchscreen where I can't actually see where I'm writing when I'm writing it. All right, but by producing that, we get what's known as a scatter plot. All right, scatter plots are very useful when we're dealing with two-parameter data. And we will come back and talk about two-parameter data later on in the course. But by and large, this semester, we're going to be looking at one-parameter data because it's a little bit more simple to work with, and it will give you the basic ideas of statistics without getting bogged down in trying to keep things straight in 2, 3, and 4 dimensions, which is sometimes necessary and never pleasant. So the scatter plot is a thing. For discussion on this, though, I want to go back to that idea of misleading graphs. All right, so fairly straightforward. Have you ever noticed that information was being presented to you in a misleading graph? If so, what did the presentation of the graph do that made the graph look misleading? And was it an honest misleading graph, or was it something being used to produce a narrative? One thing I ask in this discussion, please don't dunk on terrible graphs. I have certainly seen the graphs where things are mislabeled. Um, a very simple bar graph that I see very frequently is somebody presents something that says, uh, looking like that with yes and no, and then 32 and 57. That is not a misleading graph. That is a patently false graph, which is a very different thing. Still a problem, but I feel a lot more confident saying that a false graph is due to incompetence. A misleading graph, like the ones I talked about earlier, tends to be due to intentional malice. Not always, but tends to be. And as I've said, if somebody is going to try to mislead you with a graph, what else are they going to try to mislead you with? Always something to keep in mind as we wrap up on this video. and I'll see you next time.